and I'm also a trustee of the SCI itself. And that's a picture of me from a few years ago. My hair is even thinner than that now. And Gordon Armstrong will be the question and answer moderator. A bit about Lee. He's the Regius Professor of Chemistry in Glasgow. He's got a lot of research interests and disciplines, but there's four main aims. The first one, which is where I first came across him, was an artificial life. He's interested in the digitalization of chemistry, the use of artificial intelligence in chemistry, including the construction of wet chemical computers, and the exploration of complexity and information in chemistry. His group is organized and assembled transparently around ideas. They avoid hierarchy, and he aims to mentor researchers using problem-based approach. And his motto is, "Nothing is impossible until it is tried."
Thanks very much, David, for the great introduction. I guess everyone can see my screen. So it's a pleasure to be talking to you this afternoon about the robotic alchemist. And what I'm going to try and do the next 45 minutes, and I will keep to time to make sure we've got plenty of time for questions. So apologies in advance if I go faster than you want. What I'm going to try and do is make sure I'm slow on the points I want to make and faster on some of the details, because I'm really happy to engage in offline conversations. So if you see something you don't like, or you want to know more about, or you just don't believe, then that's fine. Just reach out. My email address, lee.cronin@glasgow.ac.uk. So we'll get going with the artificial chemist. So as David very kindly introduced in my group, I'm I started out life wanting to look at inorganic life. I realized if I wanted to make inorganic life, I needed a planet and an entire, maybe 1 million graduate students. So rather than doing that, I thought maybe we should design some new automation methods. And during that process, we worked out how to digitize chemistry. Today is a lot about that. In that process of digitizing chemistry, where we use robots to do chemistry, I realized we could also use chemistry to control computers. So I'm interested in making not just computers, not just control robots to do chemistry with computers, but actually use chemistry to do computation. And finally, I'm interested in the transition to information. So let's get on with the lecture. So what I'm going to try and talk about today is this idea called the robotic alchemist. It's meant to be a slightly tongue-in-cheek title, because alchemy is kind of that pre-chemistry or prehistory of chemistry was alchemy. Now, how did chemistry move from alchemy to, so how did modern chemistry get invented? So modern chemistry had to go from alchemy to chemistry. And I want you to think very clearly about that, that there is this gap that needs to be taken. Today, we're at the same junction where we've got modern chemistry, but artificial intelligence looms large. And right now, we are in the same domain as the alchemists. And one of the reasons why I'm presenting today, the way I'm presenting, is I want to try and prevent us from falling into that trap. Alchemists would do secret magical chemistry and move potions and things, and no one would understand how to make anything reproducible, and it was all a little bit crazy. But came along the concept of atomic number, the periodic table, and atomic relationships, and suddenly chemistry was born as a modern discipline where we could, in effect, understand and control with reason, and then we could then start to replicate people's studies. Then come to the 1900s, where simultaneously in Germany, the US and the UK, and various other places, glassware was standardized. And suddenly chemistry got its first mini digitization. And I want to carry on that theme today and say, how can we digitize now in the 2020s? So the ChemPU is the road to that digitization. And it's universal. So what I'm not trying, although I'm going to show you a lot of robots made in my laboratory and tell you that my view of the world is the best, that's not entirely relevant or necessarily true. What is relevant is the fact that we need to standardize chemistry to a correct digital language. Otherwise, we're going to be stuck in alchemy. And I think that's a very important problem I want to face head on. So we want to go from abstraction to universality. We need to have proven synthesis. If the digital code doesn't give rise to real products, then it's alchemy. And to do this, we need to establish a universal programming language for chemistry. And fortunately, this has already been done over hundreds of years. I'm not going to tell you today I've reinvented a new programming, a new way of doing chemistry. I think that that's not entirely correct. But what is correct is we need a symbolic language that is programmable, and that's what I'm going to talk to you about today. And also I'm going to talk about the information-aided chemist, material scientist, and formulator. I'm not really, and that information-aided is also automation-aided. I'm not going to be talking about autonomy in terms of completely automatic, where you get in your laboratory and you just press make me X and it makes it for you. There's so many things for chemists, material scientists, and formulators, and people working at across those disciplines to do. It's mind-blowing. And actually, I want us to think about how much time do we spend wasting time, how much of that time is wasted, sorry, on not being able to reproduce the literature, not being able to collaborate effectively, and not thinking that people's new experiments are reliable. And this is partly what happens in science. So I'm not proposing to solve science, but I am proposing to require a new standard that if you publish something and it's reproducible and reliable, that can be run forevermore. You know, what is the minimum infrastructure you need for that? So, okay, let's move on a bit. So in chemistry, abstractions already exist. And same in material science to some degree. If you take a complex molecule, knowing the laws you know, if you're an organic chemist, you can break it into reactive units using retrosynthetic analysis. And you can imagine then how to go into the laboratory and generate the fragments you need and react them together. Sure, reactions might not work because you've misunderstood the stereoelectronics, you've got the wrong solvent, or your sample's impure, or you don't have the right catalyst. Those real world things happen. But in general, most chemists will be able to make a target molecule if it doesn't break the laws of physics and chemistry in a reasonable time. But there are some limitations with that, and the limitations go to the skill level. And the big thing I want to make here, the main point, is that there is no physical instantiation in a physical synthesis system going from abstraction to synthesis. Well, not until now. What the robotic alchemist is, the digital chemist, the modern version of that, can do precisely that. So this is what I'm going to tell you about with the ChemPU. The ChemPU is a universal, it should be viewed like a Turing machine. The Turing machine in computing, those of you unfamiliar, a thing that is Turing complete, it refers to a kind of abstract idea that on it can run any computer program you can ever imagine or ever have written. So now imagine for a second a kind of a universal lab setup that can make any molecule you can imagine or any material. Now think about what you'd need for that to happen. It's not so outrageous. There might be some weird unit operations you might not do very regularly, very expensive, but you can modularize it all. So the way we wanted to design a von Neumann computer is to think about how we would leverage current advances in robotics, AI, and all the buzzwords we can put together. Because automation exists already, but what are the problems? Well, it's vendor locked. There's a barrier to entry. It's expensive. It may not be easy to program. And it has limited scope. And there's some beautiful examples out there. Peptide synthesis machines, nucleic acid synthesizers, carbohydrate synthesizers. They are all instances of what I would call, they're not universal, because you cannot make a complex natural product in a peptide synthesizer. You can't make a laser material in a peptide synthesizer, for instance. You can't make a dye, but you can make any peptide based upon the canonical 20 amino acids. So that's pretty good. But that I would compare to a single class computing machine. It's a subset of universality, but it's not universal. It can just make peptides, which I think is not bad. And so I'm not pretending today to have invented, you know, automatic chemistry. What I've kind of really pulled the blinkers off is this idea that we need to be universal, and universal isn't just a fantasy for science fiction. It is actually a requirement for progress in the science. So how do we do this in the laboratory? What happens right now? Right now, we have a written procedure. Normally, we might go in and we have an interpretation of that procedure. That's an interesting point number one. The user, the expert, will interpret that procedure, and their interpretation will be a function of their expertise. It won't be unambiguous. You won't have literally, it's not like an IKEA flat pack table or chair or bed where, you know, although I must admit I can't follow the instructions, I always get everything back to front, but if I paid attention long enough, I'd be able to make it. So because in chemistry we don't give that level of information, there is some interpretation. We do the experiment, get the result, update, and as our expertise increases, we can update our experimental method, and then we can adapt and improve everything. And we typically would develop the procedure. Let's now go to digitized. Well, we have a code. That is, we have a code which gives you everything, and then a graph. And that graph is merely where the physical resources are. Go to the weighing scales, go to the fume hood, go to the drawer, get the glassware. So those points in the graph, if you like, are located in real time and real space. You then compile to that graph and you execute. And if your code is good and your graph is good, you'll get the result. And this is the #1 take-home message for the lecture today, that if you want to go from alchemy to digital chemistry, you need to make sure that you are willing to digitize your procedure and your graph. And that may be very costly to imagine, it may be very cheap. But if you do that, I will convince you that you will be 100% reproducible all of the time forever. Except for two things: if your reagents are bad or if your hardware fails. But that's the same thing for a computer. Your computer will always work forever unless the program has a bug in it or your hardware is broken. So we're just demanding the same requirements. And so what I've also wanted to draw our attention to is this idea that we have this kind of architecture of a computer and an architecture of a computing architecture, which is kind of hybrid physical computational, which I can talk about, but it's obvious, and if you're not a computer scientist, it doesn't really matter. So why is the ChemPU needed? Well, lots of automation is out there. Some of it's very chemistry specific, such as maybe doing peptide chemistry. Some of it is workflow specific, say making a material and testing it for hydrogen evolution or something like that. Or what we want to do is try and combine those together so we have it universal, so that it isn't restricted to the chemistry and it isn't restricted to the workflow, that actually there is a more universal code we can put in to express what we want to do at a higher level. It's really like a higher level programming language, if you like. So this is the key to all of this, which is to go from robotic alchemist to a digital chemist, you need a standard programming language that is Turing complete or possible, or what I would call computable. And computation is something I'll explain at the end. And computation isn't just a term I made up to sound good. It actually means a real thing, which is going to be on consequences to every chemist and material scientist alive now and practicing chemistry in the future. So how do we get to universal chemistry? Well, the way we got there, the way we got to this truth was we realized we wanted to exploit the literature. We wanted to enable chemists and material scientists on Earth today. We want to make it modular. And we wanted to basically start an abstractable unit that we could build out to flow chemistry, or to more specific process chemistry, or to miniaturize to microfluidic chemistry. And actually, if you're thinking about how computers work using a binary code and a state machine using a clock, you actually need a state machine. And that's very technical to go into, but what does it boil down to if you're a chemist? You need to use a test tube or round bottom flask. And hey presto, as if by magic, lots of chemists and material scientists and biologists indeed and formulators work in batch to start with. And so I would argue that the round bottom flask is a transistor of chemistry. And we can build in these modules together, and with the round bottom flask, you can do any chemistry you would ever want to do. It may not be best for process intensification. It may not be best if you want to miniaturize it, but if you want to make it universal, you start with the transistor of chemistry, which is the round bottom flask. So what we did in my lab is we built the hardware that we needed to create this, this minimum unit that would abstract chemistry that we originally called the ChemPU, and we now call the chemical processing unit, the ChemPU. And the reason we built our own pumps and valves was really so we could understand the way we would compile our language to the hardware architecture. Now, we don't just have to use our pumps and valves. You can use any, as long as they are compatible with certain, or they have not compatible, have a certain specification. The compatibility comes instantly as a function of using the programming language. The ChemPU improves in versions. We've done quite a few versions now. I'm going to show you some operating in a moment. We've got lots of different modules, high throughput modules, mini modules, chromatographic modules, hardware, nanoparticle modules, formulation modules, and miniature modules, which I'll show later in the talk. Okay, so I've talked about the basis for this. In the next 30 minutes, I'm going to zip through a load of examples. So please explain to me, please don't worry if you've got questions because I go too fast. You can explain those to me and I can answer them. So the key thing to go from alchemy to digital chemistry, we need a programming language. And until my team got going on this, people kind of ignored the programming language. Why? Well, because there are really smart computer scientists who can basically make workflows for chemists. There are really smart roboticists who've got a computing language that works in robotics and digital computing. And there are really smart chemists that really want to do new operations through chemistry. So we kind of glued it all together. But the problem is, every different culture has a different set of standards, and you can never reproduce any one team's standards. And what you need to be able to do is wrap together those standards such that they naturally express the chemistry. So what I realized, in the same way that binary is kind of the machine level code for computers, and then up above that for the processor, you've got this microcode, and then above that, you have kind of the executables that get run. In chemistry, we need to understand what is our machine code, when it's literally moving liquids and solids and gases around, okay? What else is there to do? It's operating devices, closing doors, opening doors, heating, cooling, mixing, and so on. But then further up, we can express all those fundamental operations in a composite as we go further and further up our programming language. So in the end, what you want to do is go to your robot and say, make peptide involving this sequence. Do you really want to be able to type in your robot, make peptide, blah, 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 or make this molecule, and it would then make it, subject to reagents, of course, and the physical capabilities of the robot. So what we tried to do is work out how we could take the ChemPU and express the ChemPU instructions in such a way that you could make any molecule universally using the system. And actually, it didn't turn out to be that hard. We had to work out what unit operations must we have in the beginning to convince even the most skeptical organic and materials chemists that this wasn't just another very complicated robot that's going to cost too much money. And really, what is the key thing that the system needs to do? Well, it needs to be able to add stuff. It needs to be heat things up. It needs to be able to cool them down. It needs to filter, extract, wash, evaporate, do chromatography and distillation. And you can see I've made this graph here of computable procedures against module development. And in my lab right now, we've got enough modules to do 95% of all of the known chemical material science. 6 modules covers all of 60% of organic synthesis. The abstraction is universal, and there are no exceptions, right? You could say, you could come up with a fantastically hard molecule to make, or maybe a molecule that requires alchemy, you know, say make a polonium salt. Well, I mean, if I had a nuclear reactor in a digital system, I would do it. I might ask you what you want to do with the polonium and phone the police. But there are no operations out of scope. If you can think about it and write it down, you can do it because the abstraction is embodied, right? This abstraction is not a kind of, you know, if or, it really is and. So the way that works is the abstraction just understands that chemistry requires universal actions. It can now work on any robot. So if some people listening to this talk say, well, okay, I've got my own robot, my ChemSpeed, or I don't know, some kind of robot arm system or something. Can the programming language work on that? And the answer is yes. We need to might look at the API because some manufacturers kind of vendor lock things, but nothing is entirely vendor locked. And I'm confident that all the manufacturers are going to open up to this standard the same way that we've got the Sila standard, Sila 2 standard in laboratory automation. And this is the computing language is not competing with Sila 2, if you've heard of that, or any other language. This is different. This is a programming language that knows chemistry in its unit operations. And yeah, so here's an example of the chemical description language. It's a high-level description synthesis to be compiled down to low-level instructions. So there's an extract of a file there. The KDL, as we call it, gets written and compiled to a graph and then works on the robot. This all looks very, intimidating. You've got this script here, you've got this graph, and you've got this complicated robot. Actually, it couldn't be far from the truth. What we can do now is it's possible for anyone to write KDL as long as they structure their procedure correctly in English or Mandarin or French or whatever language you want, or in Scots dialect. I haven't done yet a robot in Scots dialect, but why not? It's because there is a transformer. And as long as we understand what's ambiguous and what isn't ambiguous, we can nail that down. Let me explain by showing some examples. So there's an example here of the ChemIDE interface, but I'm going to get to that and just show you a video actually. The ChemIDE is like a Python IDE, if you like. You can have an edit mode and a graph mode, and you can edit everything together and just basically then run it with a real-time mode and run your robot. But let me just show it working. So let's just say someone comes to you and says, right, I want you to take a preparation from the literature and run it on your robot without any testing. Can you do it? The answer is yes. Here's how you do it. You go to Journal of Organic Synthesis, take the text, put it into our reader, translate it into KDL, check it's correct, maybe make sure check where the syntax errors are, because there will be errors, because no natural language processing is perfect, and this is not a natural language processing system primarily. It is a chemical programming language populated by natural language processing to help the chemist. So then you basically write your program, which again is like just a few clicks. You then load in your standard graph, which is a representation of your robot that you probably would have got from your manufacturer, or you would have built and just changed a bit here and there. You then just compile your robot, the procedure to the graph. Okay, just press compile. You simulate to check it works, and then you have code that can be run on your robot. Okay, so let's see how this actually works. So what I've done so far is I've introduced the concept of computation and the need for the abstraction. I've now introduced the language and the need for the language, and now I'm going to show you the chemistry working, and we showed this in Chemify. And Chemify was a project we started to take the literature, generate the code, and then run it on a robot. And let me just show you the computer running. So now we've got that code. This is actually just building one of the first ever versions of the computer. There's lots of familiar stuff there, some unfamiliar stuff, but just take a look. The computer first self-cleans, and then does a reaction, so loads in the reagents. And then after it does a reaction, there's a workup. And every reaction has a workup, so every reaction has an isolation. Every reaction has a purification. These are the abstractions we have to have in the system. And in this case, it's all liquid. The first versions were all liquid handling, just to show for ease to get the concept there. But you can see that we've got the reaction, we've done the workup, we're now doing the isolation. And now we then produce the material. And in this case, purification is filtration, but now we use column chromatography. So wait, what we've now done is we've now shown how we can go from the concept to the language to the actual running of a robot and it making the molecules. In our first attempt, we made nitol, sildenafil, rufinamide. And again, remember the way we did this, or the way we do it now, is we can take the literature, just written text, convert it to the code. We'll get a list of reagents to buy. We put the reagents in the robot. We load it in, press go. So one robot can make any molecule. So we did 3 to start with. We was kind of like sex, drugs, and rock and roll. Well, sleeping drug, anti-seizure drug and Viagra, and that worked pretty well. But of course, we wanted to go further than this, because people were like, well, you just picked easy chemistry and the hardware doesn't work. And what I was at pains to say is that the ChemPU, or computation, isn't about our robot, it isn't about your robot, it isn't about any robot, it's about the abstraction, the absolute language that allows you to take a symbolically represented, analogically represented procedure, and then encode that symbolically into unambiguous code that you can run on any robot. So we did it. We looked across all of chemistry. We looked at CC coupling, deep protection, reduction, arylation reactions, acylation, oxidation, FGI, ring closure, heterocycles, protection, animation, so on. Within the CC bond formation, we did quite a lot at looking at the number of examples. And during lockdown last year, what my team did, I mean, I feel I'm still, I don't know how you are about lockdown, but it's still a little bit hard work, but we're really excited that we're back in the lab more. But what the organic chemists did, is we used this system and we went through the literature and we started to convert vast amounts of the literature to KDL. So when we came back to the lab, we then ran all these reactions in ChemPU. So there's now at least 50. We've now done probably about 70 different reactions in total in the ChemPU with the code. That means there are now 70 pieces of code that make 70 different molecules that will work, at least to the literature standard, forever, without any question. And that, I think, is a really interesting outcome. That if we could just, if you think about what are your 100 top materials or molecules that you want access to, to make it worth using, how many would they be and what would they be? So there's a few examples there. Totally unpublished, getting ready to publish it. The paper's going to be called Chemify, to really start to convince organic chemists that this is their friend and this automation strategy is really worthwhile. It's not replacing the organic chemist. No, it just takes the labor out of the really annoying bits. And also it allows you to go to the literature and take known reactions and know they're going to work. Because I know most organic chemists want to make new molecules, not reproduce other people's molecules, because that's a waste of time and effort and skill. To show that the ChemPU could work, we just published this paper just a few weeks ago. We basically did some cross-coupling reactions, iterative cross-coupling reactions. We did peptide synthesis, and we also made some unstable molecules, again, all in one machine with full column chromatography with our KDL code. And so I think that, and then we took the diazurine and labeled our peptide. And so that was one ChemPU was able to do a 12-step synthesis. And we're now working on routes where we can go up to 20 distinct chemical steps. We can also have inline real-time telemetry, which I can explain about in a moment, for looking at various sensors to check things are working, and also to fingerprint, to chemically fingerprint your computation. Okay, so I've got a couple more parts. I want to go into organic discovery, formulation, and then at the end talk about our nanomaterials robot. So one of the things that we want to be able to do is to have a kind of autonomous system for selecting reactions that a chemist would never do. So that basically now we've got a language, KDL, can we dream up molecules and then convert them into our language and just run them and check they work like lines of code? A bit like a programmer would just write a line of code and then run it on their processor to check it works. Can we come up with a line of code to make a molecule, check it works? If it doesn't work, we can debug it, or if it does work, we can put it in a database. And what we've got here is this workflow for generating code, putting it in our robot, executing it. We update failed runs, we assay, we keep going around this loop where we can search for more and more interesting molecules that are basically fit to a particular problem you have to solve, be it a drug problem, a material problem. Maybe you want to make an organic laser. Maybe you want to make a new perovskite. Maybe you want to make a new formulation or a new gel. So I'm going to blast through these because I just want to show you the capability and don't really want to go too much in details. There's literally 10 years worth of work and with at least 20 people. So you're talking about quite a lot of person years of work. I mean, a couple of 100 years, basically, in the next, I would say, 30 slides. So let's go. So first one here is where we had a system where we have an NMR, a mass spec, an infrared, and we put together a load of chemicals to look at their reactivity. And then by using liquid handling and a neural network, we were able to model the chemical space and just search and say, if we're able to do random reactions, can we discover something new? Now, before you worry about random reactions and safety issues, we pre-validated them with our safety officer. So although they were random to the robot and random to the user, they weren't random to the safety officer, because that wasn't kind of a professionally correct thing to do otherwise. There's another version for the setup of the reactions as we combine this with a ChemPU system to show that we can stack, do 6 reactions at once, and now we're up to 30 reactions at once. But this is not combinatorial methyl, ethyl, butyl, futyl chemistry. This is fully open-ended. Each reactor can do a completely different reaction to the other one by using a scheduler within our ChemPU. By using a neural network with the reagents, we were able to basically use NMR as a sensor. And to cut a long story short, we could train the neural network to tell us when the NMR had found interesting reactivity. And we were able to work that out by training our model and then looking at the outliers. And just to give you one example, our system was able to not only learn reactivity, but discover a reaction organic chemists would never be able to discover anything without, well, there are just too many moves required for the organic chemist to discover this. So the example was this in Tosmic, where we took Tosmic in the system. We found that Tosmic reacted with 6 moles of itself to basically go through a multi-step single substrate reaction with 5 new carbon-carbon bonds forming, involving sp-sp2 and sp-sp3, and we got a 47% yield. And that was just amazing. And if you actually look in a sample of Tosmic you might leave on the shelf, you actually can find traces of the product in the Tosmic. So it's just a little bit of oxidation and away you go. Okay, that was super quick. Apologies. Let's go on to inorganic discovery. Well, some of you might know that I'm interested in doing inorganic materials chemistry and making clusters, and also kind of new type of looking at flow batteries and hydrogen evolution. And just generally messing around and finding out what is the most complicated inorganic material I can make at the kind of solid liquid interface. The classes of molecules I'm showing here are polyoxymetalates. They're made by reducing the metal oxide at low pH, and you get reductive aggregation. You can just form loads of gigantic molecules shown in these polyhedra here, and they're all crystal structures. A few years ago, we worked out that these can self-template, and but back then we weren't really able to do automation and to really rigorously explore chemical space. So what we're doing now is we're starting to rack and screen, and a few slides here to show you how we do that. First thing is, if you've got something like a polyoxymetalate, they all use the same kind of base building blocks. They use molybdate, they use an acid, you have a reducing agent, you may have another ligand. And what we tried to do many years ago now, almost 9-10 years ago, is basically use a flow system and search through the reactor array to find new crystals. Since then, we worked out that we could not only network the robots to basically break that space up to make it easier and make the robots cheap, so you could have loads in your lab. In fact, you might have seen that these robots are so cheap and easy, they could even instruct each other what to do using Twitter. So for a few months, I had a load of robots communicating with each other on Twitter about what reactions to do, and they were collaborating using a simple code. And that was kind of a precursor to KIDEO actually just working out it would work. I got banned off Twitter a couple of times. At that time, I got banned for scientific reasons. Now I might just get banned for just being obnoxious, but that's another discussion. And so what you're able to do is have this interaction between the robot leader and the follower, but doing well-defined experiments that were owned by the cloud. And so what is important in these experiments when we went from flow to batch is we wanted to look at individual samples and look for crystallization. And crystallization for us is super important because crystallization allows us to purify the materials, identify phase pure materials, and also get the crystal structure all in one go. And that's really critical. And we were able to do that with a bunch of new clusters. And also we were able to show that we could get a human versus a random robot versus an algorithm to compete. And what we found is that the algorithm was able to beat the human and the random at searching chemical space because they didn't have any bias. It wasn't the human was inferior in terms of the reactions it chose. Operationally, it was inferior because of its bias. They thought, I wouldn't go there, I'll go there. And the bias was always wrong. So really, my message, one of the big messages today in any of your searches, if you are to do discovery science, please don't allow your bias to get the better of you. Do a random screen and be humble and question your expertise. It's quite hard to do, but it's worthwhile. And you know, probably a lot of you are working in industry and some in academia and doing science. You realise that you know, you assume that you know something and that gets questioned all the time. So it's not such a big deal. The name for this paper was called Robots v Humans. And it was so hilarious when we got it refereed because people got angry. But I used the name. Then the second follow-up to this paper was robots collaborating with humans do better. So it's like robots v humans, robots win. But then when robots collaborate with humans, you do better than the robots. So it's all a love story in the end. One of the things that we're using AI to do, and this is also unpublished, is we're making a crystal vision. And the idea is to detect the crystal and in real time look for polymorphs and new materials and really start to integrate that. I like real AI on real space, not AI on virtual space, because that doesn't mean anything, particularly if it's not digitized. There are some examples here where you can, oops, I don't know where this one is going here. So where this is up on the top here, we've got a recognizer that with one version have been able to track the crystals and another more improved one down here. But what you can see is we can use a webcam in the bottom of a flask and we can follow crystallization and also identify the crystals being formed in real time. We've also got a polymorph cracking system that I'm not going to say more about here. It's a top secret, but I've told you about it. We can crack polymorphs. Interested, come and talk to me. We're also making metal organic frameworks and other kind of materials just to see if we can use AI in building these new kind of designer materials. And MOFs are a good paradigm for that because they're so well understood. Okay, so we're going to go on to complex materials now. I've got about 7 minutes left. I'm going to try and, or six or 7 minutes left. I'm going to try and finish in that, so we've got time for questions. So now going on to complex materials, one of my first ever autonomous robots was what I call droplet robot. And what the idea was to take simple molecules, formulate them, put them into an arena, call them cells, and let them undergo some kind of evolution in the droplet world. That's our droplet west world. And then we would have a selector, which would either cause the droplet to be killed or selected. And then the successful droplets, we would then recycle back, just like in evolution. That's showing here in this movie. And they would then be used to then search physically in a new generation. And so you have this life cycle. So this is the idea to do evolution in the material world, real Darwinian evolution. And we did that and looked for different droplets and their behaviors. And just with 3 or 4 different combinations, we were able to evolve a whole new formulations. I tried to work with formulation scientists, particularly in the UK, but they just told me I didn't know what I was talking about. I thought it was really funny. It was a really good example of the drawbridge coming up in a particular area. And I think, well, that was my entire point. Of course, I don't know what I'm talking about. That's why I'm doing experiments. And formulation classically is seen as a kind of artisan, magical art. But when any area tells you they're magic, you know they're just gatekeeping. But anyway, that was a long time ago now, and we're making gel formulations, new types of active materials. So, and I have a company that I've been looking at that will kind of commercialize this actually. complex interfaces. And you can see now the way the robot works. And really, the key is not the expertise before, it's the building the robot with the expertise in mind. Now we're also making three-dimensional systems and looking at viewing. This is very high-speed droplet viewing. And you can see the droplet really moving in 3D. We've got like a number of cameras there using Raspberry Pis, getting 150 frames a second. This droplet here, you'll see will undergo a fission process, I think, at the moment. Yeah, so let's whoa, right, there we go. So the droplet goes and deforms and then undergoes a fission process, and you can see that up there and then below as well. So there's some really interesting soft matter physics you can do on these and looking at the various components. So we explored chemical space using random and curiosity-driven algorithms. So I wrote a load of AIs that would explore the space effectively. And we found droplets that would search more of the space, respond very dramatically to temperature, and really kind of give us a lot of information. And we're also not just, I've got droplets here, but we have an emulsion robot as well, and looking at biphasic systems. But because of limited amounts of time, I only showed this one. Okay, and so I'm going to close a little bit with a closed loop system. So one of the things we wanted to do was make nanoparticles using a closed loop system, and use evolution as well. But I wondered if we could go better than evolution and use a new type of approach to physically making nanomaterials using a closed loop robot. One of the ways we wanted to do this is understand how nanoparticle shapes would evolve, and think about the mathematics of that. And what we did is we came up with this idea, if you look in part A, where we would take a seed and think about how that seed could be shaped in different levels of evolution to make new types of particles. And then we modeled the feature space and explored it algorithmically to see about what morphology we could get. And this morphology will then measure spectroscopically. So the idea is to make a robot like this one here that basically would start by mixing the other reagents in the sample wheel and then explore the chemical space using UV feedback to try and get the right nanoparticle shapes in real time. So the idea is this. Number one, mix reagents in the sample vial, measure the UV and measure the pH. Okay, over time, when the UV changes and you've got your physical model which predicts that UV is reminiscent of a 50-20 nanometer particle with whatever shape, you then fit that and then you make a decision in real time to add in a new ligand or to wait a bit longer or to separate the material. Okay. We used the real-time AI to search the nanospace. We benchmarked it, sliced the phase space, explored it, and then compared. But here's a really interesting thing, and this is top secret. We haven't published this yet, but look at the results. And this is not us picking the terms. This is really just representative terms, which I couldn't believe. So I genuinely couldn't believe, because all my terms are normally crap. So we take the seed, and by adding these reagents, we then can generate these compounds. Then going from here, from L1-2, we can then make these compounds and keep going down. And you can see how the UV changes, but the robot is able to autonomously navigate the shape space. So what we've got here is the fact that the robot can make new types of nanoparticles. And yes, you guessed it, the language used to make this is also KDL. Okay, I've only got a couple of minutes, but I think you've already heard about the autonomous machine, but one of the ways we're making autonomous computer discovery machines is using this kind of approach to have a target in mind, then generate molecules that go towards that target by generating the chemical code, and we execute the code. And we've got discovery in here, and what I want to say is you've got the literature, which you prove works, but if that doesn't work properly, you use optimization, and then you can use discovery, and when you discover and you've made sure that code is good, you can then add that code into your database. That becomes a well-defined, redeployable, reusable asset. So this is kind of one of the dreams for the ChemPU for discovery. But the vision is this. I want to leave you with the vision that we want computation to be the way that we digitize chemistry. Computation is the process of running KDL code reliably on any compatible hardware. That's it, compared to computation. So it will run on Andy Cooper's hardware in Liverpool, or run on Alexi Lapkin's hardware in Cambridge, on Matt Gaunt's stuff in Cambridge, on Mimi He's stuff in Raw, on Vinda Agarwal's ChemSpeed in Bristol, on Marty Burke's cross-coupling reaction in Illinois. You guessed it, any hardware that can do chemistry and material science, this will work because it's platform universal, it's task universal, and it's chemical universal. And this is the first ever abstraction that does that. And it is the abstraction to the end all abstractions because it's Turing complete. Okay, you could make another one, but it won't be as simple because it will be Turing complete, but probably extra layers. We just made the simplest one we could. It might be we've messed something out and we haven't made it as simple as possible then, well, that's fine. But I'm happy to make it simpler. So, okay, I'm going to stop here and leave you with the socially distanced ChemPU. I'm kind of almost a minute over, but I just want to say that we want to make systems that are modular and usable at low cost. We've got implementation of all synthesis protocols. I do have a company now that is, well, I have a couple of companies actually. If you're interested in situ digitization, Deep Matter are doing really interesting things, collecting data and getting insights. If you're interested in building or getting access to robotics that will run chemical code and do discovery, then look at chemify.io. And that's got off the ground just now, and we're taking orders, only a limited number for these, what we're calling Curies, which is the first version of the ChemPU. And I think I just want to stop here by saying that we have a Matter operating system. All the stuff in the lab that we use kind of uses a common operating system, which means that things are interoperable. We can even combine formulation and organic synthesis and nanoparticle synthesis all in one workflow. So I'm going to stop there. I just want to stop by thanking, firstly, my team for their patience over the last few years and obviously their dedication through the pandemic. This is our socially distanced selfie rather than our group image that we take every October or November. And I'd like to thank all these funders for the money. And finally, I'd like to thank you for listening, and I'm happy to answer any questions. Thank you.
Thank you very much indeed, Lee. That was brilliant. I'll just give you some distance applause, and I hope everybody else does as well. I spot we've got a couple of questions. I've got some myself, but I think, Gordon, if you could deal with the ones that have come in online first, as I see there are a few.
Certainly, David. Thanks very much indeed. And Lee, thank you very much for a very, very interesting talk. First question that popped up in the course of it was the purifications that you described to us. How do they normally work? Like, for example, are they mass directed? And equally, if you have multiple reaction products, how do you isolate and analyze each product?
Yeah, so this is a really big, interesting question. We have multiple ways of doing purifications on the automation. First of all, we have a system on the Curie called the optimizer, where if you know the target you want, it will automatically optimize to maximize the product you want. And that's a first step for obviously doing your first level of purification. What we try and do is build in ways of crystallizing or precipitating the product if we can. If we can't do that, then we have an automated chromatography system where we're able to do chromatography. And in fact, what we did is we just worked with Bookie on one of their systems and made sure that KDL can program their system and you can do automated chromatography. But more important than that, we've made an AI, which is called the universal separator, which I don't want to say too much about now, but if people are interested, they can contact me. And what this AI does is it can work out how to separate anything from anything. And you guessed it, I made the abstraction of purification. And it's identifying a stationary phase, it's identifying liquid phase and the solvents you might use and work from there. You can do mass direction, but you can also just pay attention to really playing around with those process control parameters, so that when you're doing a reaction, if you have an idea in the NMR or infrared or mass spec what you're looking for, you can maximize the turnover of that sample using a series of control loops using parallel reactions. And one of the things I have done is I've done some reactions where we do 6 identical reactions, but we change all the various process parameters in real time and we optimize. And one of the things I think is really interesting is the concept of a byproduct is only, well, the concept of a product is just the one you want, right? And if you don't have any other way of getting there, then you'll just take what you have. And in chemistry, it'd be interesting to, when you have a reaction that produces many products, if you could, in general, optimize to lower the production of of the byproducts and increase the concentration of the product you want today. But wouldn't it be great if tomorrow you can change your mind? And then that would be the way to kind of attempt to move between it. But it's a big problem as well. I won't lie. But in general, the way we solve it for ChemIFI 100 has been liquid-liquid extraction and then column chromatography if we have to, if we can't do it via crystallization. So hopefully that answers the question.
Great, Lee, thank you very much. If we could turn now, the next question to following on from that is when you spoke on formulations, have you tested emulsions yet, or has it been exclusively aqueous gel formulations that you've dealt with?
No, we've made emulsions. We didn't make the emulsions intentionally to start with, but we've made some emulsions now. And I'm interested in making emulsions in our origin of life work, because we want to look at how we can make complex reaction mixtures at 2 interfaces. But we haven't just made aqueous gel formulations. We've basically made coacevates, we've made reverse micelles. We've really played around. What you can do now with the various membrane technologies is really amazing. And so I'm also trying to make a universal kind of formulator. And the universal formulator, again, is just like, how do I understand the phases and the mixtures and the separations? So what are my stabilizers, what are my surfactants, what additives, what pH, and also increasingly what redox control we can use. So the ones we've got finished are really the oil and water systems, and then the new gels, and then we've made a few kind of coacevate-like systems because we're interested in drug discovery.
Okay, thank you very much. Perhaps a more detailed technical question. One of the audience is wondering, with the pumps and the devices that your group have made yourselves for the computers, how accurate are the measurements? I suppose how reproducible are they by comparison to what a human at the bench would expect to achieve in repeating the same process over and over?
Oh, that's a good question. The accuracy, so they're much more accurate than a human because they're much less variable than a human. Some humans, paying attention, are very, very good. And of course, the accuracy is directly related to the volume dispensed and the conditions under which the technology you're using. So if you're using a Gilson pipette that's being calibrated to one level, then of course you're going to get high level of accuracy. What we wanted to know is when we're using our syringe pumps, in general, what concentrations must you run at to make sure that you've got the reactions reproducible and you're not suffering from any problems. And we haven't run into any problems at all. In fact, our pumps, I wanted to make the pumps universal for doing microfluidic synthesis because, believe it or not, we got money from UK Space, and we've made a concept for a space ChemPU, and also we've got plans for sending a mini version of the computer, which we've got in a box about this big, that will eventually go to Mars or go on a SpaceX thing. That's the idea, right? Elon Musk is not going to Mars without a chemistry lab. And so we really needed to look at the volume sizes and whether that was even feasible. But yeah, it works pretty well. If you can't control if your volumes become less accurate because of the way you're operating the size of your syringes, then you change your concentration, okay? And I think that seems pretty obvious when you think about it, but human beings, okay, work at the most convenient level, whereas your system can be changed relatively easily. The hardest thing, I think, in the system is really weighing out the solids at the beginning and working out how to minimize the manual solid handling. But that's another discussion, I suspect.
Indeed, may lead into the next question, which is when there are unexpected failures or faults, the like of a seized pump, a blocked line, a reagent that's not up to standard, how does the system deal with those kind of exceptions? The sort of thing that would cause the blue screen of death if you were running it on a PC.
So we have a lot of, the idea in the future is if you've got mission critical reactions to happen with a high value material, then what you might want to do is find a way of validating your reagent. And in the same way you validate your protocols in various things, you do a pre-flight check for your reagents. So, and then if you've then got unexpected mechanical failure, one of the things we've been doing in one of our systems is having a fallback liquid handling route. So if something fouls, that the system detects a blockage and then it goes to the backup line where it goes and cleans the other line. And we're starting to play with that. And you can see how that's easy to implement conceptually. It's a little bit of a difficulty fiddly, but because now we have complete video inside the fume hood, we have sensors over all the reactors. We have conductivity sensors, pressure sensors, RGB sensors, and so on. And they're all integrated into the ChemPU. We can see when things go wrong. And so rather than getting a blue screen of death, you get an exception. And if you can pause the system, if it's possible to pause it, or just pause and say, please, I'm paused, user intervention required. Because what we can make sure is that the user's material is prioritized at all times. Because if you're doing a really long reaction, and let's imagine you're making a natural product and you're 50 steps in, and you've got to make the system reliable. So there are various routes we're looking at that. But of course, we're very early. But just imagine that the first digital computers were when they were using the solid state, the valve transistors. There were valves blowing every few minutes, right? And the ChemPU feels a bit like that right now. There's always one burning dumpster in the lab, and so, but because we're not my company Chemify is making the hardware, but really Chemify is about establishing the standard and getting everyone to adopt it. But the hardware will get better and better and better over time. Right now, we just need to demonstrate the concept works. The other thing that's important we realize is, like in the automotive industry, you need to understand the lifetime and the aging of your materials. And what you can do is you can do preventative maintenance. You don't wait until your syringe breaks. You don't wait until your valve is corroded. You just change them. And we work out, how many 100 hours of timing you get. And with that kind of preventive maintenance, that gets rid of so many problems. I just can't believe it. And mainly when your reagents go down, I'll tell you one thing, is that actually because you've made them up. What we used to is that when you normally do chemistry, you make up your solution just before you need it. In the computer, because you might not, in the ChemPU, sorry, you might not do it for a few days, right? Everything's made up at the beginning of the week. But what we do now is we don't make up the solutions until they're needed automatically, and the solid is handled in a little reagent hotel under nitrogen. And the final thing to say there was even got an organometallic computer now, which does full shape line operations, all under digital control, which is kind of cool.
Yes, indeed. Thank you very much for that. Now, one final question, and on a completely different tack, we have one of the participants asking if they wanted to apply to join your group. How would they go about that, please?
Email me. Basically, email me and send me a CV or just an introduction of why you're interested, and I'll do my best to consider. I'm always looking for talented people who are motivated, and also people wanting to expand their talents. So you may feel they're not entirely qualified yet, but maybe they're a great synthetic chemist, or they're a great, gel chemist or something. So I would say to people, don't be shy, just ask. The worst I can say is, sorry, I don't have funding right now, or the lab is too full, but I'm always on the lookout for new people. So please contact me.
Thank you very much indeed. And with that, can I hand you back to David, please?
Yeah, well, thank you very much. Applause again, Lee. That was brilliant. I have a few questions myself, but we're running out of time, so I will ask them by email, I think, later on.
Okay, well, that's great. Well, thank you so much for having me, and sorry for the screen sharing hiccup at the beginning, but we nailed that pretty quick, and I hope that was okay.
Oh, it's absolutely brilliant. Thank you very much indeed. And so we just a few more things, a sort of bit of pep talk about the SCI and why people, if they're not already members of the SCI, should join. I think it's a brilliant organization. Our house magazine is called Chemistry and Industry. You will get preferential rates on conferences and networking events. There's student scholarships and travel bursaries. Get discounts on books and journals published by Wiley. The Business Centre in Belgrave Square you can use free of charge. Discounted rates on room hire in the central London location. You can present at SCI conferences or write for the journals or magazines. A very good networking organisation. I really do say that very strongly, a brilliantly networking organisation. And then you can get e-alerts and bulletins based on the your own particular scientific interests. So that's all from us for now, and there's a few upcoming events. And there's one, in fact, tomorrow, which I'm going to make sure I watch, which is where Dame Jocelyn Bell Burnell is talking about interstellar chemistry. I think that should be a brilliant talk. And for those coming in from Ireland, she has a strong Irish connection as well. And then next week, the Fine Chemicals group have a postgraduate symposium. And then on the 12th of May, there's a careers event for the agri-food supply chain. And then on the 24th to 25th of May, the Scotland group is having an afternoon of science and careers. So thank you all very much indeed. I hope you've enjoyed it. I certainly have, and hope to see you again at SCI events in the near future. Bye for now.